What's up, guys? This is Mr. Chap. We're going to do a chemistry review for your test tomorrow. All right. So the test tomorrow is going to cover everything that we've learned in the fourth 6 weeks, and everything in chemistry, starting from like what atoms are made of, all the way up until what we learned yesterday. Okay. So, first of all, I've added some memes into this. Never trust an atom because they make up everything. So atoms make up everything. Atoms are the building block of life. So let's start with atomic structure. So some of the main things that you need to know is that atoms are made up of subatomic particles. Sub means smaller than or below. Atomic means atoms. So they're the things that make up atoms. Protons. Protons are the positively charged subatomic particles. So their protons are positive. That's what we remember. You guys made a cheat sheet. Make sure that you have that cheat sheet available, right? So protons are positive. They're located inside the nucleus. So they're located in the middle here. And they're included in the atom's mass because they have a mass of 1 AMU. So they have a mass. The atomic number on a periodic table tile will tell you the number of protons. And this is important. This is really important. This determines the atom's identity. So if I have one proton, an atom with one proton is going to be hydrogen. If I have more than one proton, it's no longer hydrogen. If I have two protons, it's now helium. So I liken this to your like lunch number, right? If your lunch number is a certain number, if you added one to it, it's no longer your lunch number. If you subtracted one, no longer your lunch number. This is the identity. So all atoms of, let's say, carbon have the same number of protons. They can have different number of electrons, they can have different numbers of neutrons, but they all have the same number of protons. So this is very important. Protons determine the element's identity, what it is, its lunch number. Neutrons. Neutrons are neutral. They have no charge. Neutrons, neutral, neutrons, no charge. They're located inside the nucleus along with the protons. So in the nucleus we have protons and neutrons. PAN, pan, protons and neutrons. And they are also included in the atom's mass. A pan has mass, like a frying pan, a cast iron pan. You don't want to get hit by it, so it has mass. It would hurt, right? So one neutron also has the atomic mass of 1 AMU. So protons and neutrons make up the mass. They both have mass. Sometimes this is the same as the number of neutrons, but not always. You have to use 8-man to figure that out. Electrons. Electrons are the last subatomic particle. They're negatively charged. And the way you think about this is electrons, the flow of electrons is electricity. If you touch electricity, it will have a negative effect on you. It's not good, right? You don't like to touch electricity. So electrons are negatively charged. They're located on the outside in the shells. They do not contribute to the atom's mass. So they are 1/2000th of an AMU. Protons and neutrons are 1 AMU. These are 1/2000th of the size. So very, 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 very small. So they're so small that they don't add to the mass of the atom. 1/2000th of an AMU. And in a neutral atom, which is what we've been talking about, the number of protons equals the number of electrons. The number of protons equals the number of electrons, and that's 8-man. A equals P equals E. Atomic number equals the number of protons equals the number of electrons, which is my next slide. So from the periodic table, the atomic number equals the number of protons and the number of electrons. So that's how you find the number of protons and electrons. And then to find the number of neutrons, you have to use man. Mass minus atomic number equals the number of neutrons. So here we would have 6 as the atomic number, 12 as the mass. So the atomic number is 6. So the atomic number 6 equals 6 protons equals 6 electrons. And the mass is 12. So 12 minus 6 gives me my number of neutrons, which is also 6. 2 helium atoms were acting funny. Hee hee. Because helium is He. So He. Funny. It's a funny joke. Okay, so now we're on to the next unit, periodic table and reactivity. Main things that you need to know are the valence electrons. Valence electrons determine reactivity. So protons determine the identity, whether it's a hydrogen or helium or lithium or beryllium. Valence electrons, the electrons on the very outside, is what determines how reactive it is. So a valence electron is one on the outer shells of the atom. So here, copper, Cu, has 1 valence electron. The number of valence electrons determines the element's reactivity. And I believe I go over this in another slide, but on the periodic table, if you have 1 valence electron or 7 valence electrons, your atom is very reactive, it's highly reactive. If you have 8 valence electrons, or if you're full, your atom is stable, not reactive at all, inert. Okay, you'll need to know on the test your periods versus your groups. And I told you guys to remember period, right? And when you do period, you do a motion with your hands from left to right. So periods are left to right. They're rows. The periods on the periodic table are numbered from 1 to 7. 1, 2, 3, 4, 5, 6, 7. So this is period 1, left to right. Period 2, left to right. Period 3, left to right. Period 4, period 5, period 6, period 7. So here, this is period 5. Those in the same period have the same number of shells, the same number of circles. If you were to draw a Bohr model, the same number of circles that you draw around it. So this has 5 shells or energy levels. They're the same thing. So we made a cheat sheet using this, and if you have it, make sure that you have it available when you take your test. Chemical properties are not similar. So rubidium is not necessarily the same as I think that's strontium. I have no idea what Y is. I probably should have picked a higher one. It's not the same as xenon or iodine or tellurium or I don't know what that one is actually. All right. So on the periodic table we have periods, period, left and right, and groups. Groups and families, they're the same thing. They're synonyms. They're the same thing. So groups and families go up and down. So this is group 15 or 5A. Groups and families on the periodic table are numbered from 1 to 18. We like to talk about 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These have the same number of valence electrons. So everything in group 15 or 5A, it doesn't say 5A there, but on your periodic table it should. Groups in 5A all have 5 valence electrons. Nitrogen has 5 valence electrons. Phosphorus has 5 valence electrons. Acetine has 5 valence electrons. I think that's tin has 5 valence electrons. So everything in this column has 5 valence electrons. Groups 1A and 7A are the most reactive. So this one right here, my alkali metals, which are the ones that I showed you the video of them kind of exploding a bathtub and exploding a little tank. And then over here, 7A or 17, they are the most reactive. Group 8A or 18 are not reactive at all. They are called inert or stable. So these are the noble gases right here. Alright, next we went over metals, nonmetals, and metalloids. And I pulled out the specific few specific slides about where they're located on the periodic table and their some of their physical properties. So most of the elements on the periodic table is metal. So everything on we mostly talk about the zigzag. It starts at boron. Boron is the boron at the top of the stairs. So we have this zigzag right here. And anything on the left side are metals. So all of these are metals. If you forget, just think of a metal. Like think of, let's say, iron. Iron is definitely a metal. It's right there, Fe. Or maybe you think of silver. Silver is a metal, Ag. Or you think of gold. Gold is a metal, Au. So everything on this side are metals. So most of the periodic table is metals. The 88 elements to the left of the stair step line are metals or metal-like elements. Most of these are solid at room temperature. The only one that's not is Hg right here. That's mercury. That's a liquid metal. Physical properties of metal: they have luster, so they're shiny. They're good conductors of heat and electricity. They're high density, so they're heavy for their size. They have a high melting point, so it takes a lot of heat to melt them. They're ductile, meaning they can be pulled into wires. And they're malleable, meaning that they can be hammered like a mallet. They can be hammered into thin sheets like aluminum foil. Next, we have nonmetals. Nonmetals are basically the opposite of metals. They're on the other side of the stair step. So we have that zigzag on the in the middle, and they're on the other side. They're on the right side. So we have very few nonmetals. Their properties are the opposite of metals, and most of these are gases at room temperature. So like these are gases: oxygen, fluorine, nitrogen. These are gases. So if you forget, you know that oxygen is a gas. We need oxygen to live. We need oxygen to breathe. So you find oxygen, and you know that is a non-metal because we can't breathe metals. Physical properties of nonmetals: they're opposite of the metals. So usually they have no luster, meaning they're very dull. They're not shiny at all. They're poor conductors of electricity and heat, so they're good good insulators. So electricity doesn't flow through them well. They are brittle. They break easily. So this is the opposite of malleable. Malleable, you hit it with a hammer, it squishes. Here, if you hit it with a hammer, it's going to break. They are not ductile, so they can't be pulled into wires. They're not malleable, so that if you hit it with a hammer, it's not going to squish, it's going to break. They're low density, so mostly they're pretty light. A lot of them are gases. Those are obviously going to be light. And they have a low melting point. So a lot of these are going to be gases at room temperature, so most of them are, a lot of them are not solid at very high temperatures. Okay, so metalloids. Metalloids are on the zigzag. They're marked in gray over here, or in silver. They're elements on both sides of the zigzag line that have properties of both metals and nonmetals. Boron is a boron at the top of the stairs, so it starts at boron and it kind of squiggles down. They share properties of metals and nonmetals, so they're all solids. They can be shiny or they can be dull. They are ductile. They can be pulled into wires. They're malleable. They can be squished with a hammer, and they conduct electricity better than metals, or better than nonmetals, but not as well as metals. So that's why they're important in electronics, in like cell phones and computers and stuff like that, when you need to be able to control how much electricity is going through it. Here's another meme. I told a chemistry joke. There was no reaction. Get it? Because reaction, yeah, okay. Alright, so counting elements and atoms. So this is what I went over before I had to leave. So an element is a chemical that cannot not be broken down into any other substances. So these are things on the periodic table, right? So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, all those things. each element has a unique capital letter that represents a different element. So here we have C6H12O6. This is glucose. This is what is in it's part of photosynthesis. It's the sugar that's created by plants. And so to figure out how many elements, if the question is asking you how many elements there are, you underline all the capital letters. So we have underline C, underline H, underline O, and that means that we have 3 elements. We have carbon, we have hydrogen, we have oxygen. Right there. So sometimes these will have just one capital letter, sometimes it will have a capital letter and a lowercase letter. Every once in a while, I don't think in this class, but every once in a while there'll be 3 letters and it'll be capital, lowercase, lowercase. Okay? Subscripts. So subscripts are the small numbers. Sub means small, sub means below. So they're the small numbers after the elements symbol right there. So H2, that 2 is a subscript. This tells me how many atoms there are. I bolded that on purpose. So subscripts tell the number of atoms. Okay? This is important because we're going to go over what tells me the number of molecules. So subscript tells me the number of atoms. Here we have 2 atoms of hydrogen. No subscript. So over here we have H2O. There's no subscript on the O. That means that there's 1 atom present. You don't have to add in 1. You don't add a 1. It's going to look weird. So if there is none, no subscript, none means 1. If it meant 0, a lot of my kids say that and think that it means 0. If it meant 0, I would just not put that O, right? So because I have that O, that means there's at least 1, so it means that there is 1 because there's no subscript behind it. So here we have H2O. H has a subscript of 2, that means there's 2 hydrogen atoms, the red ones. O has no subscript, so that means there's 1 oxygen. So here is my oxygen. 2 hydrogens, 1 oxygen. Alright, so now I add this big number right here. This is number 2. Okay, this number 2 in front of H2O. I have H2O, which is water, which we have right there, right? 2 H2O means I have 2 molecules of water. So H2O is a molecule, I just have 2 of them. So this is a coefficient. This big number is a coefficient. The big number at the beginning of this formula is a coefficient. It means that I have 2 molecules of water. So I have water over here, and then I have another molecule of water over here. So big thing you need to know is that subscripts, small number, tells me my number of atoms. The coefficient, my big number, tells me the number of molecules. So when you're counting atoms, you have 2 H2O here. First thing you need to do is underline the capital letters, H and O. Then you're going to write your elements. So underneath here, I will write H equals O equals. Then I would cover up my coefficient. So that number 2, I would just pretend it doesn't exist. So now I have H2O. Then you're going to count the atoms using the subscripts, H2 and O. Then you're going to multiply at the end everything by that coefficient. So let me show you. I think I can draw on here. Okay. So first thing I do is I underline my capital letters. Second thing I do, oh man, is it going to disappear on me? Oh man, okay, I guess I'm not going to do that. Alright, so next thing I would do is I would write H equals and O equals. Then I would cover up my 2, pretend it doesn't exist, and then I'm going to look at H. H has a subscript behind it of 2, so I have 2 H's. And O has no subscript, so it means I have 1 O, 1 oxygen. Then I uncover my coefficient, I have a 2, and I multiply everything by the 2. So I have an H equals 2, I multiply that by 2, so I have 4 hydrogens. I have an O. O has, we only have 1 O, so I multiply that by 2. We have 2 oxygens. 1 times 2 is 2, right? You can also, if you want to draw it out, I wouldn't suggest doing it this way, but if it makes sense to you and the other way doesn't, you could draw out H2O and H2O, and then you're going to count your hydrogens, I have 1, 2, 3, 4 hydrogens. Oxygen, I have 1, 2 oxygens. That's how you do it. Okay, so while I was gone, you guys went over evidence of chemical changes. And this is my main slide for this. So this is a foldable we normally do in class. You put it in your IMB. I also print it out and put it on the wall. This is a picture of the one that was put on the wall. It's torn because, I don't know. I'm terrible at taping, I guess. All right, so our acronym that we remember, our mnemonic that we remember for the evidences of a chemical change are city girls love their phones. So these are things that if you look at, if you have do an experiment and you look at it and you see one of these things, you may have evidence that a chemical change has happened. You may have evidence that a new property or new substance has been formed. So C stands for color change. So this is an unexpected color change. If you have a red liquid, you add a blue liquid and it turns green, that means you may have a chemical change. Girls, the G stands for gas formation. If you have bubbles form, if it gets fizzy, like Alka-Seltzer or like baking soda and vinegar, you have gas forming. That may tell you that you have a chemical change. L stands for light production. That means that it's giving off light. Things that give off light are fire, sparks, or like glow sticks. T stands for temperature change. This means that the temperature went up or the temperature went down, but it was unexpected. Like if you boil some water, it's obviously going to go up, right? The temperature is going to go up. That doesn't mean that we have a chemical change. But if you take a cold liquid or a room temperature liquid, mix it with another cold liquid or room temperature liquid, and it suddenly starts to boil, that means that you had an unexpected temperature change. So you're going to likely have a chemical change. If you take another liquid, you mix them together, and it suddenly starts getting really cold, right? That also means that there was likely a chemical change based on the temperature change. Lastly, we have a precipitate formation. The P stands for precipitate. Precipitate means that a solid is formed where there was no solid before. This can either happen when two liquids combine or a liquid and a solid combine. And so here we have a beaker with some red liquid, a beaker with some yellow liquid. When I mix them together, some solid forms at the bottom. So this can be a solid like a crystal or something like that, like salt or sugar or something like that, forms at the bottom of it. It can also be that the mixture got cloudy, and if you waited long enough, like the soda bottle that I showed you, if you waited long enough, it would settle to the bottom as like sludge, basically, like gross stuff. But that means a precipitate is formed. I told you guys that a lot of my kids get confused between precipitate and precipitation. Precipitation is when snow or rain falls. Here, you would have a solid form which is denser, so it would also fall. So that's another way to think about it. All right. So my last slide is about the law of conservation of mass or law of conservation of matter. They mean the same thing. On one side, I have my reactants, and then I have my arrow, and I have my products. RAP, reactants, arrow, products. On this side, I have CH4, I have 2O2. On this side, on my product side, I have CO2, and I have 2H2O. So if I were to count these out, count my atoms, I would underline my capital letters. I have C, H, and O. C would equal 1 because I have no subscript behind it. H would equal 4 because I have a subscript behind it. O would equal 2 times that big 2, so I had 4 oxygens. So 1, 4, and 4. Now if I counted on this side, if this adheres, if this follows the law of conservation of mass, this side should be exactly the same, right? I'm going to rearrange them, but I cannot create or destroy atoms. I can just rearrange them. So here I have C, I only have one C. So that would be the same over here. So over here I have 1, 4, and 4. Over here I have oxygen. Oxygen, I have 2 oxygens over here. I have 1 oxygen times that 2 coefficient. So I have two oxygens over here. I add them together. I have 4 oxygens. With hydrogen, I have 2 hydrogens over here. Multiply by that 2. I have 4 hydrogens over here. So on this side I have 1, 4, and 4. On this side I have 1, 4, and 4. So this equation is balanced because this equation has the same number of carbon atoms, has the same number of hydrogen atoms, has the same number of oxygen atoms as this side. This side has the same number of carbon atoms, has the same number of hydrogen atoms, has the same number of oxygen atoms. So when you have a reaction in real life, when you have a reaction, you're never going to lose anything, you're never going to gain anything. It's just going to rearrange. Alright, so I hope this video was very helpful for you. I hope this video helped you in case you missed some time or you didn't understand some of the concepts that we went over in our class. And I just want to make sure that you have a nice review and have good luck on your test tomorrow. Alright, have a good day, guys.